Let's continue with our discussion of Discovered, Not Designed, by Sean McClure. Today is the second part of our interpretation. In the previous section, we divided problems into two types. One type is the so-called difficult problems. These are complicated and composed of many parts, but you can solve them through design, using a many-to-many approach. For example, when building a large bridge, as long as you break it down layer by layer into modules, you can stack knowledge and solve it. Every step in the solution is clear, logical, and explainable. That is design. The other type is hard problems. These are so complex that no designed, logically deducible solution exists. Naturally, you might think, hard problems must be much harder than difficult problems. Actually, not necessarily. Today we reveal a major insight. Hard problems not only have solutions, but the solutions are often surprisingly simple once discovered. And once you do discover them, they can be executed with astonishing speed and effectiveness. If you take away just one upgraded understanding from this section, let it be this: complexity is not a burden. It is an advantage. When we encounter complexity or a hard problem, we should actually be excited. Because in sufficiently hard systems, there may exist elegant, even magical solutions. Let's start with a problem sitting somewhere between a difficult problem and a hard problem. The Rubik's Cube. Have you ever played with one? You're facing a cube with scrambled colors. How do you restore each face to a uniform, orderly color? There are 3 ways to solve a Rubik's Cube. First, the beginner's method. Strictly following rules. The most common beginner method is layer by layer. You memorize 7 or 8 algorithms. First solve the 4 corners of the first layer, then the 4 edges of the second layer. Follow the rules step by step and you will always get the cube solved. This method is logical, interpretable, and easy to explain. A typical designed approach. Its drawback: slow. Second, the expert human method. When you are very familiar with Rubik's cubes, you remember many common configurations. When you see a pattern, you intuitively know what move will transform it into another pattern you recognize. And from there the solution is nearly automatic. This is like professional chess players recognizing familiar shapes and sequences. The speed is extremely fast. Third, the AI method. It doesn't use human-invented rules or learned algorithms. It relies purely on intuition. It takes the cube's current state as input and, who knows what it is thinking, produces the solution almost instantly. Similar to AlphaZero playing Go, some operations are incomprehensible to humans, yet they are fast and accurate. A group of MIT students built a robotic arm powered by machine learning that can solve a Rubik's Cube in 0.38 seconds. This is awe-inspiring. Imagine it. Mechanical power driven not by fixed rules, but by intuition. And that is precisely how AI large language models work. It is also how humans recognize faces. It is how we solve all hard problems. Why can't hard problems be solved through design? To answer that, we need to understand 3 spaces. The possibility space, the feature space, and the solution space. Take the Rubik's Cube again. The 6 faces allow for an enormous number of color combinations. Every possible sequence of moves combined with every possible cube state forms a massive set. This is the possibility space. For Go, all legal moves across the entire game sequence form another vast possibility space. But no human considers the entire space. What we actually consider is the feature space. The feature space is the subset of possibilities that seem meaningful or promising. In Go, when facing a board position, a player can intuitively identify moves that look good. The subset of plausible candidates is the feature space. McClure gives the example of designing winter gloves. All materials and shapes form the possibility space. But in practice you only consider dimensions like thickness, fluffiness, absorbency, and strength. Those dimensions define the feature space. And the correct solutions, the few patterns that actually work, form the solution space, a tiny subset of the feature space. So why are hard problems hard? Because 1. There are no clear causal relationships within the feature space. Many elements contradict each other. Better insulation means less flexibility. A good Go move forbids certain follow-ups. 2. The solution space is tiny. The feature space is already tiny compared to the possibility space, making brute force search impossible. In computer science, these are NP-hard problems. No efficient algorithm exists to compute the solution in reasonable time. Therefore, you cannot design the solution. Rubik's cubes and Go still aren't the hardest problems. Their possibility spaces, while huge, are still finite. But real-world hard problems have infinite possibility spaces. Consider a cheetah hunting in the wild. Its environment is endlessly variable. Its feature space, the plausible things it must consider, is extremely high-dimensional and interdependent. A cheetah is far harder than a cube or a Go board. Yet nature found the cheetah's solution. The cheetah functions beautifully. But we cannot fully understand the cheetah. We may summarize some behavioral principles, but we can never articulate precisely how its brain works or how its muscles coordinate. In many ways, the cheetah is a black box. But here is the key insight. Hard problems do have solutions. But they cannot be designed. They must be discovered. And the tools for discovering them are: 1. Pattern recognition. A high-level abstraction ability. The power to grasp the shared essence behind different appearances. You recognize the faces of family and friends despite changes in makeup, weight, fatigue, swelling, or lighting. You do not measure nose width or eyebrow length. You simply know. This is compression of information, the extraction of stable patterns amid noise. A neural network does this too. And it is a black box. 2. Heuristics. Simple rules of thumb, shortcuts, instincts. Emotions are heuristics. Fear run, affinity approach. They are not precise and sometimes wrong, but generally useful. With pattern recognition plus heuristics, you have direction inside the fog. Then you try, fail, adjust, refine. This is soft search. Guided trial and error, not brute force. Like neural network training, your internal model iterates until it becomes sharp and effective. The final model is complex. And must be. Only complexity can meet complexity. Let's use archery as an example of a skill that must be learned. Archery looks like something that could be solved by design. A set of instructions. How to grip, pull, aim. But these key techniques are heuristics. They tell you roughly what to do. In real combat, you can't calculate bow angle, newtons of force, arc trajectory, and impact point at 15.73 meters. You feel it. That feeling is a neural network model built from training. Learning archery means solving a hard problem. Traditionally, people believe this method yields only approximate solutions. A compromise due to the limits of human precision. But McClure makes a major conceptual update. This is not an approximation. This is the correct solution. This is the optimal way to solve a hard problem. Yes, you don't hit the bullseye every time. But nature does not require perfection. There is no absolute precision in the real world. You do not need the global optimal solution. Only a good, workable one. Training plus iteration plus trial and error plus pattern recognition is the right path. Hard problem solutions have 3 characteristics. 1. Once found, they are extremely fast. Face recognition is instant. Archery in battle is instinctive. No manual, no step-by-step logic. The situation is complex, but the execution is crisp. 2. They are highly flexible. A cheetah can hunt, defend territory, find shelter, avoid parasites, and adapt to temperature changes. Once its internal model is trained, it can operate in diverse, uncertain, even chaotic environments. By these 2 features, hard problem solutions are better than designed solutions. A human archer is far more adaptable than a robot runner. A cheetah is far more advanced than any bridge or airplane. 3. They are not explainable. You cannot precisely describe how you made a shot. A master archer cannot simply lecture a student into mastery. The real learning happens inside the student. The internal model is tacit, not verbal. We ultimately obtain a feeling. And feeling is far more advanced than procedure. Today AI is helping us solve hard problems. Using reinforcement learning to control plasma shape in fusion reactors. Autonomous driving. Discovering new molecules. Predicting protein folding. These were long-standing unsolved problems. The reason? We used to rely on design. Now we rely on discovery. Solutions that emerge from variation, iteration, selection. And the wonderful news is, once a good solution is found, its execution is fast and excellent. Einstein once said, God is subtle, but not malicious. He was right. But more than that, nature is generous. The more complex the system, the more likely it is to contain efficient, elegant, beautiful solutions. Complexity is not a curse. It is a blessing. Once you realize this, you'll see that most of the problems we solved in the past were artificially simplified. Distortions of nature. We have never been able to face truly hard problems until now. Why do complex systems contain brilliant solutions? Because complex systems are interesting systems. Their most fascinating property is emergence. We'll discuss emergence in the next section. That's it for today's content. Thank you for watching, and I'll see you in the next video.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.